Hi, I'm Laís Esperanza and I'm going to present how to use life cycle assessment to analyze the sustainability of integrated mode traffic aquaculture. So first, I'd like to define integrated mode traffic aquaculture, IMTA. That is the production of aquatic organisms from two or more trophic groups connected by nutrient flows and are fully or partially harvested to facilitate the ecological balance. So as you can see in this image, you have internal flows from and to different organisms um, that are connecting the systems. And why we want to load these systems? As you know, the population there is growing, and with that, the demand for food and other resources also is growing. What can generate the depletion of the environment when you're doing this in large scale and without controls? So we need sustainable solutions for that. For example, the ecosystem would be able to address several goals to the sustainable development of the world as defined by the United Nations, such as the zero hunger, the life below water, and responsible consumption and production. Furthermore, it could have an indirect positive impact in several other goals, as, for example, good and healthy well-being, clean water and sanitation, sustainable cities and consumable, and others. Considering all this potential, we need to be able to evaluate the real sustainability of the system. So to do that, we use the life cycle assessment, or LCA. There is a methodology to evaluate the potential impact of a product or system based on the ISO 1440 and 14044 standards, and also the International Reference Life Cycle Data System and other methodologies and documents from European Union and other organizations. So we do that to assess the environmental and social impacts of a system or product in order to evaluate or compare them to all your life cycle. So cradle to grave, we can say that, like since the source to disposal recycling. With that, we can identify the impact hotspot and assess the strength and weakness of the process to know where to improve it. And to perform that, we follow this four-step methodology that is defined in the standards of ISO. So first we define the goal and scope LCA of the LCA, and then we collect the data in the inventory. And as we perform the impact assessment, and all these three steps they are all passed to interpretation and evaluation, and then you can have these direct applications of this LCA as product development, improvement, strategic planning, policy making, marketing, and others. So starting with the goal and scope definition. First, we need to understand the intended application of the study. So such is for a simple assessment or a comparison, and what approach we are going to be taking. The audience, the system's boundaries, so it is cradle to grave, well to gate, where we're going to stop and start the analysis, the data that you're going to require for that, the functional unit that will be used to assess, so that can be mass, energy, cost of the terminal product or a fraction of it. And beside of that, all the assumptions and limitations of the design production system. In the case of the integrate, we define the boundary of income, finish at the product gates, that is the production of fish, oyster, and algae. And we evaluate four different scenarios. There are three already studied at Integrate 1 by IPMA, the semi-intensive INTA, the polyculture, and the semi-extensive INTA at Cetaqua, and the alga plus alga production and now at the extension of the project. And the functional unit is 1 ton of aquatic product, mainly fish and oyster, with the impact allocated by mass. After the definition of the goal scope, we need to collect the system data and make the life cycle inventory. So what we should include as our input and output. So As input, it's important to include the infrastructure and the equipment use, as well as the land used and the prior uses of that. The fries or lava and the feed, including compositions and source. The consumables, as the chemicals, product packages, all the water amounts and its quality, and finally the energy and fuels used by type and source. And as output, the products, there would be fish, oyster, algae, and any other, and water discharge and emissions to the system. So in the integrator systems model in the farm system with all the physical inputs that I stated before, and the output as dead fish, waste packaging, and rejects. So it's important to note that in the first phase, the seaweed was considered as a downstream associate production, but it's going to be part of the main products from now on, especially in the alga plus scenario. So after collecting direct data of the production, it's important to understand all the impact associated with it, like in the background. So we use some international available database such as Equinvent, that is the most famous one, but there is also many others available online and in the literature. So these databases are important to understand the impact behind each input and output of the system. With the complete inventory and modeling, we can start to make the impact assessment, where the results are presented divided by impact categories. One example of category is the climate change or global warming. So you can be indicated by greenhouse gas emissions using CO2 equivalent as characterization factor. The impacts can be presented as midpoints, so when they're like climate change, human toxicity, like ecotoxicity, land use, and others, or endpoints when they are grouped to give more general impact numbers, such as grade on human health, natural environmental, or natural resources impact. The methods to normalize, group, or weight the impact categories can vary a lot, and there are more than 40 methods in the database and literature to be doing this kind of presentation of the impacts. So the most used ones are recipe, CML, IPCC, and many others. Usually we use the recipe that are one of the most famous, and for example, only that has 18 categories, including the agricultural land occupation, climate change, freshwater, marine and terrestrial toxicity, fossil water depletion, and many others. And to help in these calculations, there are several softwares, such as OpenLCA, YABI, or CIMAPRO. Each one has its advantages or disadvantages. While one has a better interface, the other gives more background details or even allow easier modeling. Also, there are some free, some are paid, so depending of what you're looking for. In Green Collab, you use the OpenLCA, that is an open source software that allows to modify the background data and understand a little bit more the origin of each impact category. So for you to be able to understand how we present this analysis, I chose two results from the Integrate one. And the project chose 7 impact categories as presented in X, including the global warming, eutrophication potential, and water dependence. The first graph compared the impact between the systems evaluating the project, while in the second graph, we see the analysis of the weight of each source of the impact inside the categories. For example, the fish feed, that is the brown one, has the biggest impact in global warming, but the rejects impact more in the eutrophication potential, that is the green one. So it's important to evaluate where we should concentrate our efforts to decrease the global impact. So the last step on that would be the interpretation of these results. So to understand if the data methods and assumptions are correct and make sense. And when you're doing that, we can identify several challenges in the quality of our methodology or data, considering the baseline, the construction, the correct location, the scale up factor, so different things can cause uncertainty in the process. And with the results, we also can suggest some improvements to the system. In the IMTA case, I can point out four main that can be stressed already. The first one would be this search for more sustainable feed for the fish. The second would be the diversification of products such algae and sea cucumber that is not only producing fish and oyster, but the system with more products to have the allocation in more outputs. The water recirculation when the systems are doing separate points, and the renewable source of energy fuels that would also decrease the impact of the systems. And just want to say that these metrics can help to evaluate the sustainability and maybe to add in the future certification able to assess the ecosystem service of this type of system. This kind of certification needs to include the quality data for all inputs and outputs, effluent and fit characteristics, chemical use, and any influence on the ecosystem as escape and interactions to the environment. So in conclusion, to the future, integrate one to apply the LCA to other IMTA systems, creating specific background and standard methods in order to evaluate the ecosystem services by a proposed eco-label. I would like to finish the presentation acknowledging all the participants of this project, especially IPMA and CETAQUA for addressing the first LCA models, the Cherna to help me to developing the OpenLC models on Green Collab, and the work package 5 that was dedicated to this work formed by WALC, Bangor University, Green Collab, and also Alga Plus that is providing the data to the second phase of the project. So thank you very much. And if you have any questions, you always can send me an email on esperanza@greencollab.com.